All right. So again, my name's Charlie. I'm the Astronomy Outreach Coordinator here at the Vanderbilt Planetarium. So good evening. Thank you for having me, and thank you all for showing up. So now tonight we'll be talking all about debris with this hopefully impactful presentation, Meteoroids, Meteors, and Meteorites, oh my. So now, when it comes to space debris, there's a lot of different classifications. So I figured I'd start off, but just by differentiating all these different objects. So for example, first we have comets, then there are asteroids and meteoroids, and there are meteors and meteorites. So I wanted to start off first by talking about comets. And throughout this presentation, I like to make it interactive, so I'll be asking you guys some questions. Feel free to just call your answers out. If you guys have questions, feel free to stop me along the way. So first question for everyone is does anyone recognize this comet?
Yeah.
All right. I forgot the name. Yeah, it does have a long name. So this is, well, it has a long name and a short name, both not very easy to remember. So this is Comet 67P Churyumov-Gerasimenko. Yes. So this is also, easier name is known as Chury. Now, so comets are rocky and icy objects in our solar system. Now, comets can be anywhere from a few hundred meters wide to tens of kilometers wide. Now, for a better idea of what that really means, so a skyscraper, like for example, the Empire State Building, is about 443 meters tall, and Mount Everest is around 9 kilometers tall. So a comet can be anywhere from the size of a skyscraper to multiple times the size of Mount Everest. Now, in this picture here, you might notice that there appear to be these kind of streams coming off of Chury. So now, Comet Chury here, since it is made of ice, as it interacts with the sun's rays, that ice will not melt, but it will sublimate, meaning it turns directly into gas. So we can see these streams of gas coming off of this comet here. Now, so Comet Chury is about 4 kilometers across, and it takes around 6.5 years to complete one orbit around our sun. Now, this comet was also visited by a spacecraft. Does anyone know which spacecraft might have visited this comet? It was a fairly famous mission I remember back when I was in college. Maybe not. All right, so I'm getting an idea of what you guys know about space debris. Okay, so now Comet 67P was visited by the Rosetta spacecraft, which was carrying a lander known as Philae. And this was pretty big in the news at the time. So the Rosetta spacecraft was launched in 2004, took about 10 years to reach this comet, so it reached Chury in 2014. And the lander, named Philae, attached to Rosetta, was detached from Rosetta and sent down to land on Chury here. But unfortunately, its landing gear malfunctioned, so it bounced off of Chury. And because of very weak gravity there, it eventually bounced into a very shady region. The next unfortunate part, it was powered by solar panels. So, so Philae lost power and we lost contact with it. But the fortunate thing about this landing, thank you, Ken. So the fortunate thing about this landing is that Chury did eventually rotate around and bring Philae into the sunlight, so we were able to regain contact with this spacecraft pretty briefly. Now, so I mentioned here that Chury is about 4 kilometers wide this way here, and that's a little bit hard to picture. So to put that into perspective, here's Chury compared to the Los Angeles skyline. So really an enormous object, about half the height of Mount Everest. So you can imagine if this were to crash into Earth, we'd be done for. Now, so comets here, or actually a little bit more about the Rosetta spacecraft. So even though we had some struggles with the Philae lander, the Rosetta spacecraft was able to discover some pretty cool things about Chury here. So for example, Chury, since it does have a lot of ice, a lot of that ice, or a lot of its composition, is frozen water. But it's not water like we find here on Earth, not H2O. So the water on Chury is known as heavy water, meaning that the hydrogen in that water is actually an isotope of hydrogen called deuterium. So the water, the frozen water on this comet is sometimes called D2O, so deuterium-2 oxygen. Now, so a little bit more about the Rosetta spacecraft. It returned some pretty cool images of this comet here. So here we have some images from Rosetta orbiting around Comet Chury here. Yeah, this is one of my favorite animations in all of astronomy. Now, this video we see here, so I mentioned that comets are made up of a lot of ice. And this makes it look almost like there's a snow flurry happening on Chury right now, so it's pretty appropriate. But these little dots and streaks that we're seeing on the screen here, in the background, those are all stars in the background. You can even see a star cluster in the top left corner there. There it goes, zip. And all these other little streaks of light up in the foreground, those come from cosmic rays interacting with Churi's cameras and detectors. So although it does look a whole lot like snow, it's stars and cosmic rays we can see in this animation here. So far from what we've seen in this comet, comets are pretty similar to asteroids, just big rocks in space. But what really distinguishes a comet from an asteroid would be its tail. And here we have Comet Neowise. How many of you got to see Neowise back in 2020? All right, yeah, me too. That was the first comet I ever got to see. Unfortunately, I didn't get any pictures of it, so this is somebody else's picture here. But here we have Comet Neowise, which passed around the sun in 2020. Now, to talk a little bit more about the anatomy of a comet's tail here. So right at the center of the comet is the nucleus. That's the solid, rocky, and icy part of a comet, which is surrounded by the coma, which is basically like an atmosphere around that solid comet. And then we have the tail, which could sometimes separate into two different tails, and you might even see some more complex shaped tails than this. For example, Comet ZTF, that rare green comet that passed a couple of years ago. How many of you guys got to see that one? Yeah, a few of us. So comets can sometimes have different colors. They can have some complex shapes to their tails. But a lot of the time you will see two separate tails. One known as a dust tail, so you can probably figure it's made of a lot of dust. And then also the ion tail here. So what forms a comet's tail is the solar wind. So these high energy charged particles constantly streaming away from the sun. As they interact with the nucleus of a comet, that causes those ices to sublimate, which then loosens rock and dust on the surface of the comet. And then that dust just gets left behind in space as one tail. And all that gas that has now been sublimated from that ice becomes the ion tail. And energy from those solar particles can even ionize that gas, meaning strip them of their electrons. So here we have our ionized ion tail, which is the gas, and here we have the dust left behind by the comet. Now, so I didn't take this picture, but I wanted to show you some pictures that I did get of a comet. So here we have, and it's hard to see, but I'll point it out. Here's a picture of Comet Tsushinchan Atlas, or Comet 2023-A3. Did anyone see this one? All right, excellent. So now this picture I took from Astronomical in Northport, and if you're not sure where Astronomical is, if you look out across the water, that first strip of land before Connecticut, that is Astronomical. Now, so in this picture here, it's pretty difficult to see, but that little wisp of light right at the center, that is the comet. So it was visible to the naked eye, and I got this picture in, let's see, October of 2024, so this past October. And I took this picture with just my cell phone, so I did have to increase the exposure time a little bit, but it was visible to the naked eye. And if I were to zoom in on that picture, you might be able to see it a little bit easier. So there's that little wisp of light, our comet there. And yes, yeah. And I was also fortunate enough to have my telescope on me at the time. So I had a little 2-inch telescope, and I got this picture of Comet 2023.
Oh, wow.
Yeah. So you can really see there's the coma, and here we have the tail right behind it, extending up towards the top of the image there.
And that was with your cell phone?
Through a 2-inch telescope, yeah. Yeah. So you really don't need any advanced technology to get great astronomical photos. I'm really just getting started with astrophotography myself, mostly just with my cell phone right now. All right, now. Yeah, yeah. Expensive hobby. Now, yeah, this was at Ashokan. Yeah, so it was a great view. I think we were looking towards the west, so this was right after sunset. All right, now. So I mentioned before that, so comets' tails, they form because of the solar wind, those particles coming off of the sun. So as a comet orbits around the sun, now one other distinguishing thing about comets is that they have very highly eccentric orbits, meaning they're not very round, they're more oval or elliptical shaped like this. So they start far off in our solar system, swing by pretty close to the sun, and then get flung far back out into the solar system. So as comets orbit around our sun, as they get closer and closer, that solar wind starts to interact with the nucleus of a comet. and then the tail starts to form. But a comet's tail, since it's formed by solar wind, will always point away from the sun. So in this image here, we've got our two tails. We've got our dust tail there again, and our ion tail. So the ion tail will always pretty much point directly away from the sun. The dust tail, you might notice, will curve a little bit away from the ion tail, because once that dust is released, the comet moves a little bit further this way. So it seems to have more of a curved shape to it. So as the comet continues its orbit, again, that tail will continue to point away from the sun, and as we get closer and closer to the sun, the tail will get larger and brighter. Now, I said earlier that comets can be anywhere around tens of kilometers, right? Yes, tens of kilometers wide, but a comet's tail can be millions of kilometers long. And we usually have about 2 chances to see a comet as it's coming closer to the sun and heading back out towards the edge of the solar system. And comets can come from a couple different regions of our solar system. So we'll start with the farthest possible region. Does anyone know what this part of our solar system is called? Right, so here we have our Oort cloud, which is still actually theoretical. There aren't really any direct observations of objects in the Oort cloud yet, because, well, the Oort cloud, we think, extends from about, let's see, 2,000 AU away from the sun to maybe up to 200,000 AU from the sun. For a better idea of how far that is, that's about halfway to the next closest star, Proxima Centauri. Now, so in the Oort cloud here, there could possibly be trillions of comets, all these rocky and icy objects. And somewhere in between the Oort cloud and our solar system, in what some people call the inner Oort cloud, we can actually find another dwarf planet, which I didn't know about until I made this presentation, called Sedna. And so Sedna, it takes about 11,400 years to complete one orbit around the sun, and its aphelion distance, meaning the greatest distance between Sedna and the sun, is 937 AU. And to give you a better idea of how far these things are away from our sun, Neptune is about 30 AU away from the sun. So these objects are tens of times further away from the sun than our farthest planet. And also down here, this little inset, that blue dot, that is Neptune's orbit that we're looking at. So there's Neptune right at the center, with the Oort cloud, this spherical cloud surrounding our solar system. Now, comets that come from this region of our solar system, they could take anywhere from a few hundred years to orbit the sun to maybe even millions of years. Now, even though we haven't directly observed any objects in the Oort cloud, the fact that there are comets that have orbits that have such a long period is evidence that this Oort cloud exists. Now, if we were to take a look at a region a bit closer to the middle of our solar system, so in this image here, so here we have the sun at the center, there's Jupiter, Saturn, Uranus, and Neptune. Now this region, does anyone know what this one is called? Right around the edge of Neptune. Right, so here we have our Kuiper belt. So this is where we can find our favorite dwarf planet, Pluto. Pluto is among these objects here. Now, the Kuiper belt here extends from about 30 to 55 AU away from the sun. So really, right around Neptune's orbit there, and then further out. Now, in this picture, oh, and I'll also let you know these numbers, this is the scale of our solar system in AU. Now, all these different colored dots here represent different kinds of objects. So now right here around Jupiter, these gray dots, those are known as the Trojans. So those are asteroids that orbit the sun along with Jupiter around Jupiter's Lagrange points, which are basically regions of space that are influenced by Jupiter's gravity. So Jupiter basically carries these asteroids around with it around our sun. Then, a little bit further out, all these green points, those are these centaurs, which are objects with unstable orbits around our sun. And these objects may have been pulled in from the outer solar system by the gravitational influence of our gas giant planets here. Then these purple objects, you'll see just a few of them spread throughout the Kuiper belt. Those are the Neptune Trojans, so they're controlled by Neptune's Lagrange points. And here we have these blue dots are our Kuiper belt objects. So these are objects with stable orbits around their sun, and those are mostly comets and, again, our favorite dwarf planet, Pluto. Then you'll also see these kind of tan dots, which are resonant Kuiper belt objects. Now, one of the cool things about objects orbiting the sun and gravity is that sometimes their orbital periods will line up with each other. They'll kind of match up with each other, which is why they're called resonant. So for example, these kind of tan dots, let's say for every one time that those go around the sun, Neptune will go around twice. So there's this integer ratio between how long it takes Neptune to orbit and how long it takes one of those resonant Kuiper Belt objects to orbit. Or maybe it would be something like for every 3 times Neptune orbits, one of these will complete 2 orbits. And that is the ratio that Pluto has with Neptune. So Pluto is one of these resonant Kuiper Belt objects. So as Neptune passes by these resonant objects, it exerts a little bit of a gravitational tug on those objects and keeps them in a stable orbit. So if it weren't for that resonance, that ratio between their orbits, these objects might have unstable orbits and could possibly be flung out of the solar system or pulled further in, becoming centaurs like these. And then finally, this other kind of pea soup green that we have around the edge here, those are scattered disk objects. So those, you can see they overlap with the Kuiper Belt, but they don't have stable orbits, so they could possibly be pulled further in and become centaurs like I was saying before. Now, as we look at this picture here, the Kuiper Belt is called a belt, and this image looks a lot like it's shaped like a disk. But Kuiper Belt objects, their orbits can be inclined compared to the plane of our solar system. So for example, here we have Pluto's orbit tilted out of the solar system there. So the Kuiper Belt isn't really shaped like a belt, it's shaped more like a torus or like a donut like you guys were eating earlier. Yeah. All right, now we're going to zoom in even further, get closer to the center of our solar system. Oh, and I should say, so in the Kuiper Belt there, I'll actually go back a little bit. So in the Kuiper Belt here, so comets that originate from the Kuiper Belt, their orbits could be just a few years long. And one of the most famous comets, the Halley's Comet, comes from the Kuiper Belt, whose orbit is around 75 years, I think it was. So Halley's Comet was last seen in 1986 and will be seen here again in 2061, so mark your calendars. Now, so the shortest period comet that we know of is called Comet Encke, and it comes from this region in the Kuiper Belt. And Encke's orbit is only about 3 years, and we think Comet Encke is the progenitor, or the originator of the Taurids meteor shower, and we'll be talking more about meteor showers a little bit later on. But now we'll zoom in closer to the center. So here we have our inner planets. So this red ring right there, that is Mars's orbit. There's the sun at the center. And then we've got Jupiter and Saturn, the yellow and green lines there. So here we have our asteroid belt, which are these kind of orange dots here. And these bluish dots are near-Earth objects. So the asteroid belt is where we can find most asteroids in our solar system. And it extends between about 2 and 4 AU away from the sun. And we think that there's around 2 million asteroids larger than 1 kilometer wide inside our asteroid belt. And then there's millions of smaller objects and innumerable even smaller objects. So now the asteroid belt here is where we can find another dwarf planet called Ceres. And even though there are millions of asteroids, so the dwarf planet Ceres, or let's see, right, so even though there are millions of asteroids, the entire mass of the asteroid belt is only about 3% the mass of our moon. And of that, 40% of that mass is the dwarf planet Ceres. So the rest of the 60% of our asteroid belt is just these smaller asteroids. Now, so our near-Earth objects here, these blue points of light, that's any object that comes within 1.3 AU of our sun. And Earth orbits at about 1 AU. So these are objects that you hear about in the news a whole lot. And there's about 37,000 known near-Earth objects. But anytime you see some kind of headline that says, oh, there's an asteroid, it's coming towards the Earth, usually at its closest approach, it's still millions of kilometers away. So normally not something to worry about. All right, now, I want to focus on just a handful of asteroids in our asteroid belt here. All right, and does anyone recognize any of these? And if not, that's all right, they're big gray rocks. So, so these asteroids here, now, these were the targets of some other space missions that you may or may not have heard of recently. So I mentioned that Ceres, that dwarf planet, makes up about 40% of the mass of our asteroid belt. Over here on the right is the largest known asteroid called Vesta, which makes up about 7% of the mass of our asteroid belt. Now, Vesta was visited by a spacecraft called Dawn, and Dawn discovered that there may have been even flowing water on Vesta's surface at one point. And over here, now, I'll actually ask by show of hands, how many of you have heard of Bennu before? All right, excellent. So this is the asteroid Bennu. So this is the target of another very recent space mission. So, yes, OSIRIS-REx. So this was visited by the spacecraft OSIRIS-REx. So OSIRIS-REx, let's see, and I have the year it made it to this asteroid. Let's see, OSIRIS-REx reached Bennu in 2018 and touched down on Bennu's surface and even collected a sample of this asteroid's surface material and was able to return that material here to Earth. So OSIRIS-REx performed a flyby of the Earth and dropped a canister here on Earth containing some parts of this asteroid Bennu. And upon the first inspection of this material, we found some organic molecules in that material, so molecules that would be necessary for life. All right. Right, yeah, exactly. Now, and that was, let's see, and that was in 2023 when that canister was returned to Earth here. And then OSIRIS-REx continued on and is now going to be studying some other near-Earth objects or other asteroids. And then finally, over here on the left, these two objects are Didymus and Dimorphos. And I think I'm pronouncing those right, but I'm not too sure. So these two are near-Earth objects, which were visited by something called the DART mission. So DART, it stands for the Double Asteroid Redirection Test. And the goal of this mission was basically to crash a spacecraft into Dimorphos there and see if we can change its trajectory. So this is a moonlet, so a moon of an asteroid, and we wanted to see if we could change its orbit around this asteroid Didymus. And it turned out we were pretty successful in doing that. So now, why would we want to crash a spacecraft into an asteroid? Well, we wanted to see if we could change its trajectory. So let's say if there were an asteroid that were on a collision course with Earth, we want to either be able to redirect it or at least slow it down enough so that Earth has time to get out of the way. Because we do want to prevent these impacts. No matter how rare they are, we want to be prepared for that possibility. So this image here was taken by the DART mission, let's see, in September of 2022. And I just want to I have a number here, but it's blocked by Zoom, so I just want to get my number here for you. There we go, now I can see it. So this was taken 2.5 minutes before impact at 570 miles away. All right, now this next picture I have for you. So this was taken 11 seconds before impact, 42 miles away. And 3 seconds, 11 miles away. And here is 2 seconds, 7.5 miles away from the surface of Didymus, or yeah, Dimorphos, excuse me. So this is the last full image we got from the DART mission before impact. So you can see this asteroid is basically just a loose collection of rock. All right, now. So we've been talking all about rocks in outer space, but who knows, what do we call a space rock that has landed on Earth? Yeah, you guys are meteor correct. So now next, let's talk about meteorites. And a lot of you guys might be familiar with that meteorite just over to your left. So here we have a picture of the meteorite right here in our very own lobby. For anyone that might not have read that sign before, so this is a 60-pound metallic meteorite made mostly of iron and nickel. It's around 4.7 billion years old, and we think it landed on Earth around 100,000 years ago. Now, meteorites, they're classified based on their composition. Now, only about 6% of meteorites are metallic like this one, made of iron and nickel. The other 94% are stony meteorites. So they're made of things like silicates, very similar to what sand is made of. Now, So meteorites, sometimes they're very similar to Earth rocks, and there's a few characteristics you want to look for to try to identify a meteorite. So especially looking at this one here, you'll see it has all these kind of round indents on its surface called regmaglyphs. So those come from the meteorite falling through Earth's atmosphere and some material being evaporated away, leaving behind these gaps. So if you find a rock that looks like someone was kneading a ball of clay, those are regmaglyphs, could possibly be a meteorite. Now, one of the other things you want to test is it magnetic? Now, even stony meteorites might be slightly magnetic. So if you have a rock that looks like it has regmaglyphs and it's a little bit magnetic, better chances that it could be a meteorite. But now if we take a look at stony meteorites, how do we tell those apart from regular Earth rocks? So if we were to cut open a stony meteorite, there are some that you'll see have these kind of bubbles of material in them, and these are called chondrules. So if you see a meteorite like this with chondrules in it, this is known as a chondritic meteorite. So these little bubbles of material, those first formed at the very beginning of our solar system, over 4.5 billion years ago. So early on in our solar system, a lot of material was just molten rock floating around in these hot little bubbles of either rock or metal. And those little molten bubbles started piling up on top of each other, becoming bigger and bigger rocks, eventually becoming meteoroids and asteroids, and so on, even up to planets. And I just remembered, so I should mention, so we've been talking about asteroids. So asteroids can be between about 1 meter wide and about 1,000 kilometers wide. Anything bigger would probably be a dwarf planet. A meteoroid would be anything smaller than a meter wide. All right, so just wanted to get that in before we continued about meteorites. So meteorites here, if you find a meteorite like this, you just found a rock that hasn't changed since the beginning of our solar system, over 4.5 billion years ago. And you'll also notice meteorites tend to have this outer layer called a fusion crust. So basically, the outer layer will melt as that rock falls through our atmosphere, creating this kind of crust around it. So if you find a rock that has chondrules and a fusion crust on its outside, then you probably found a meteorite. But not all stony meteorites are chondritic like this one. So of our stony meteorites, let's see, 86% are chondritic like this one. Let's see, and then another 8%, I should say, of all meteorites, 86% are stony chondritic meteorites and 8% are achondritic. So an achondritic meteorite like this one is practically indistinguishable from any other normal Earth rock. So what can you look for to tell if you have an achondritic meteorite? Well, one, you can look for those regmaglyphs, those kind of curved indents. You could look for a fusion crust on its outside. But with these kinds of meteorites, these didn't form at the beginning of our solar system. They formed later on. So these kinds of meteorites originate from other rocky objects in our solar system, like planets, moons, or large asteroids. So what that means is, so these kinds of meteorites, they were at some point hot enough that their material melted and started mixing together and became part of a planet, basically. So how did a rock that was part of another planet end up here on Earth? Any guesses? Dave? Yeah, from an impact. So there are some meteorites here on Earth that we know come from the moon and Mars that made it here because of an object impacting either the moon or Mars. So basically, another asteroid crashing into the moon flung material out into outer space, and some of it eventually landed here on Earth. So the only way that we can really distinguish whether an object came from the moon or Mars is with some pretty advanced mineralogical tests, so determining what its composition is. All right, now, speaking of impacts, so here we have a pretty famous crater here on Earth. Has anyone visited this crater? All right, excellent. Yeah, so this is Barringer Crater, sometimes also called Meteor Crater Park. So this is in Arizona, and this crater is about, let's see, and I have the numbers written down here. I've got a lot of numbers, and I can't remember them all. And so let's see, I think it's a bit smaller than that. And yeah, so this crater is only about 1 kilometer wide, but you might be right, that could be its circumference, about 3.5 miles. That sounds about right. And it's around 170 meters deep here. Now, This crater was formed around 50,000 years ago. And to us, that sounds like a long time, but in geological terms, that's nothing. This is a baby crater. Now, the Earth has been hit by asteroids and comets and meteoroids just about as many times as the Moon has, or any other planet in our solar system, but we've only identified about or less than 200 craters here on Earth. So part of the reason for that is that, well, Earth has an atmosphere that protects us from a lot of smaller objects. We're also mostly covered in water. And we also have erosion here on Earth from weather or even plate tectonics that can take the Earth's crust and renew it over time. So this crater here, being only 50,000 years old, hasn't experienced a whole lot of erosion. So this looks pretty much the same as it did when it first formed. And especially being in the middle of a desert, there's very little weather, there's very little rain or erosion there. And this crater was formed, let's see, and I have the size of the object. This was formed by a nickel iron meteorite that's about 50 meters wide. So something, to put that in American terms, about half the size of a football field created something about 3/4 of a mile wide. All right, now, so these kinds of impacts are incredibly rare. But when they happen, they can cause extinction events, just like with the dinosaurs 66 million years ago. But we have had some close calls with space debris, even in recent times. So does anyone remember, let's see, around 2013, there was a pretty big explosion or impact. Does anyone remember where that happened? Right, yeah, so that happened in Russia, in Chelyabinsk, Russia. So here we have a video of that meteorite exploding in Earth's atmosphere. And so this happened February 15th, 2013. So this meteorite exploded in the atmosphere over Russia. And so this explosion happened, let's see, about 18.5 miles above Chelyabinsk. And this was caused by a meteorite that's about 20 meters in diameter, which is about the size of our theater here. Now, so this explosion, here you go, I have some more numbers for you. And just a moment. Just some of these windows on Zoom are a little bit in the way. All right, I guess I won't get them out of the way. So let's see if I remember the number right. So this explosion was about 30 times more powerful than the nuclear bomb dropped on Hiroshima. So an extremely powerful explosion. And this kind of explosion here is called and I believe it's pronounced either bolide or bolide. I think I've heard it both ways, bolide. All right. So here we have a bolide, this explosion happening over Russia. Now, around 1,500 people reported injuries. Not really direct injuries from the explosion, but mostly indirect because of broken glass. So the shock wave from this explosion caused a lot of windows to be blown out, even caused some buildings' roofs to collapse. And so somewhere around 7,000 buildings experienced damage from this explosion over an area about half the size of Long Island. All right, now, so I want to show you guys a pretty cool video that I found recently. So now these kinds of events are pretty rare, and only one now. Let's see, I want to say only one person is ever reported to have been hit directly by a meteorite. I'll talk a little bit more about her in a second. But watch in this corner. So this might be the first video ever captured of a meteorite fall right outside someone's front door, and it was captured by one of those Ring front door cameras. Now, and I think I'll mute it now after that, or I'll pause it here. All right, so now it's very rare for anyone to be hit by a meteorite. As I said, only one person's ever reported to have been hit by a meteorite. Let's see. Oh, and this recording, just so you guys know, this was taken July 25th, 2024 on Prince Edward Island in Canada. And the only person that was ever hit by a meteorite, her name was Anne, there we go, Anne Hodges of Silicoga, Alabama. So the story goes that she was lying on her couch in her living room, and a meteorite fell through her ceiling, hit her radio, and bounced off the radio and hit her thigh, and caused a pretty big bruise on her thigh. And that's the only reported contact between, or impact between a meteorite and a person in human history so far. All right, and that was in, let's see, November 30th, 1954. All right, so now even though meteors or meteoroids, meteorites, they can cause some damage, even cause injury, it's very rare, and usually we actually get treated to something pretty nice by these meteorites. So we get to see meteor showers. Yes. Yeah. Let's see the one that hit the woman in the thigh. Oh, from the video there. I don't know the exact size, unfortunately, but yeah, I would say,
I think about softball size.
Good.
I'm not sure.
It sounds about right. Yeah. Yeah. Yes, we can watch it one more time. I think I can play it. Yeah, so it should play again one more time, I think. Yeah, there we go. Yeah. Yeah. Yeah, so usually, as space debris enters Earth's atmosphere, we normally get treated to meteor showers or meteors or shooting stars. So, now, meteor showers, there are some that occur annually. And that's because as comets orbit around the sun, they leave behind these trails of debris. So they have those dust tails, they leave behind plenty of dust. And as the Earth orbits around the sun, it'll sometimes pass through those trails of debris. And as that debris enters Earth's atmosphere, it burns up and appears to fly across the sky as a meteor or shooting star. And so again, they can happen annually, depending on when the Earth passes through this trail of debris here. Now, let's see, the next meteor shower is coming up, or I'll talk a little bit more about one specific meteor shower, the Geminids, which is one of the most prolific meteor showers, sometimes generating over 100 meteors per hour on a nice, clear, dark night. Now, meteor showers, they get their name based on which constellation the meteors appear to be flying out of. So for example, the Geminids meteor shower appears to come from the constellation Gemini the Twins, which is visible in the wintertime. And all meteor showers, they have what's known as a radiant, a point in the sky where all the meteors will appear to be flying out of. So for the Geminids meteor shower, it might look something a little bit like this. So you'll notice all the meteors will appear to move away from that radiant there. And so meteors usually last, I'd say, less than a second, but some can last a little bit longer, maybe a couple seconds. They all have varying brightness and even sometimes different colors. Now, I think one of the most amazing meteors that I've ever seen, see, I can't unfortunately remember when it happened, but I remember I was driving around Huntington, Northport, and I saw this extremely bright green meteor just shoot across the sky and took up almost the entire sky, and it was in the sky for at least a couple seconds. So one of the most amazing things I'd ever seen. But a meteor's color can tell you a little bit about what that object was made of. So for example, if you see a yellowish meteor, that might have been composed mainly of iron. If you see that it's a little bit orange, that might mean it's composed of sodium. A bit of a purple color comes from calcium. A bit of a bluish green color comes from magnesium. And if you see kind of a reddish color, that oxygen or nitrogen there might actually be from not the meteor itself, but the air around the meteor heating up. And if there's a mix of chemicals, you might even see a mix of colors there. All right, now some of the next meteor showers coming up, or at least some of the most prominent ones. So coming up this summer, we have the Perseids, which will reach its peak on August 12th, the night of August 12th this year. Now, meteor showers, they can last anywhere from a few days to several weeks, but there's always a peak where they're most active. So here we have just the peak dates when they're most active. And for the Perseids, unfortunately this year, so there is going to be, I think during its peak, it's going to be pretty close to a full moon or a waning gibbous moon. So the brightness of the moon is going to wash out a lot of those dimmer meteors. So unfortunately, not going to be a great show from the Perseids this year. But then coming up after that are the Orionids, which originate from Orion, which reaches its peak on October 21st. And then we have the Geminids, December 14th, 2025. And I didn't look into the moon phases for those, but you guys can figure that out. All right, now, so we've been talking a whole lot about natural space debris, but now I want to talk a little bit more about man-made space debris. So here we have a map of all known pieces of man-made space debris larger than 1 millimeter orbiting around the Earth. So here we have millions of objects. Around 12,000 of those are operational satellites. And out of those satellites, over 8,000 were launched by the United States, 7,500 of which are Starlink satellites. So Starlink satellites make up most of the operational satellites in orbit around the Earth right now. And you'll see that there's a few different layers of satellites here. We've got our low Earth orbit satellites, and here's our geostationary orbit satellites, satellites that are far enough away from the Earth that they orbit once for each time that Earth orbits, so they actually appear to stay still in the sky. And that allows us to observe one part of the Earth for a long period of time. Now, so with these objects here, this image is not to scale. So even though this seems really crowded, most of this is empty space. So usually we don't need to worry about collisions, but collisions do happen. So for example, let's see, here we have two Russian satellites. Here we have the Iridium 33, which at the time was operational. And here we have a Cosmos satellite, and I have the number for that too, Cosmos 2251. So the Cosmos satellite here was not operational, and these two satellites collided with each other and generated about 2,000 more pieces of debris that were all about 10 centimeters wide, which is about the size of my palm. So imagine 2,000 things the size of my palm or larger, orbiting at tens of thousands of miles per hour around our Earth. So when collisions like this happen, they contribute to something called the Kessler syndrome. So a theory proposed by Donald Kessler in the 1970s, saying that as we launch more and more objects into space, and as there are more and more collisions, there's going to be kind of a cascade effect, leading to more and more collisions in the future, which at worst will make future space travel impossible. But luckily, we're not at that point just yet. Now, so I want to show you another example of a collision. So here we have the Endeavour shuttle. Now these doors here, those are some thermal or radiator panels there. And here we have a hole caused by either a man-made piece of debris, so one of those little chunks of a broken up satellite, or it could have been a micrometeoroid, which created a hole that's about 5 millimeters wide. And here we have the exit hole. So this object was going tens of thousands of miles per hour when it hit the space shuttle Endeavour. And so if we go back to that picture of the shuttle, so the space shuttle, or a space shuttle program, was responsible for launching the International Space Station out into orbit, as well as the Hubble Space Telescope. So astronauts often had to work in this part of the shuttle, often with those payload doors open. So you could just imagine what might happen to a person if they got hit by a micrometeoroid at tens of thousands of miles per hour. All right, but now we'll continue on. So we have these thousands of pieces, or even millions of pieces of debris all orbiting around the Earth right now. And some companies, or with most of these satellites here, we have to manually maneuver them to avoid collisions. So let's see, the ESA. Okay. Yeah, so the ESA, the European Space Agency, is currently tracking all of its satellites, all of its hundreds of satellites, and each satellite can get multiple or hundreds of alerts per week about potential collisions with space debris or other satellites. Now, normally only a couple of those will actually need any kind of attention, where the probability of collision is high enough that they need to plan some kind of a maneuver to move the satellite out of the way and avoid a collision. Now, so the ESA is also looking into the possibility of using machine learning to automate this process. But right now we're having humans analyze the possibility of collision and then planning a maneuver, which then also needs to ensure that they don't maneuver the satellite into the way of another satellite. So we're looking into machine learning to make this all automated. But some private companies, including ClearSpace, they're planning on launching spacecraft up to grab other spacecraft and deorbit them. So they're planning some spacecraft with these robotic arms or even nets to catch defunct satellites that are currently orbiting around the Earth, and then drag them into the Earth's atmosphere and eventually cause them to burn up. Now, a lot of satellites in Earth's low Earth orbit, they can deorbit on their own and eventually burn up in Earth's atmosphere. But for some of those satellites, even in low Earth orbit, it could take decades for them to eventually fall out of orbit and burn up. So it would be better for us to clean up outer space than just wait for them to fall on their own. And really the best option is that anytime we send something into outer space, we need to make a plan for when it will eventually deorbit. So we can't just send things into outer space willy-nilly. We need to make sure we're planning for how we're going to clean up outer space after ourselves.
Does the device that deorbits go down with the satellite, or is it just send it and then it goes looking for more?
So I believe the plan is to really lock onto, especially with this one, with these robotic arms, I think the plan is to lock onto larger pieces of debris and then both burn up in Earth's atmosphere together. And that would really be ideal because let's say maybe something with this spacecraft with these arms failed on its way into outer space. Now we just have another broken satellite up in outer space. So the best plan would really be for, if we're going to take this course of action, would be for this spacecraft that's grabbing the defunct satellites to also burn up with these objects that it's catching. All right, so there we have just about everything I've got about both natural and man-made space debris. So I want to thank you guys for being a great audience, and I hope you enjoyed.